Okay, so in this video we're going to look at solutions of the Dirac equation. So here's the Dirac equation. And we're going to take the easy way out and just assume a form for the solution that happens to be the correct form, which will be this spinor u that only depends on momentum times this exponential term. And then we'll have another solution that also just has the spinor v, only depends on momentum times this other exponential term. And if we plug this in, we get this thing, which can be, and then we can write this, this operator in matrix form like this, where I've used the notation I talked about last time, the sigma mu, which is just, so sigma 0 is the identity, and then sigma I are the Pauli matrices, and then similarly sigma bar is identity with minus the Pauli matrices. And so using that notation, I can write this operator really nicely like this. And so this is what my, my equation reduces to. So we need to find a u that satisfies this. And so basically the answer is this. So u can be any spinor that looks like square root of p dot sigma times this two-component spinor. I don't know what this letter is called, just squiggly. But it's some two-component spinor, and the top half, and then the bottom half is this thing multiplied by the same spinor. So it doesn't matter what this two-component spinor is, as long as our four-component spinor basically has, two of the same spinors stacked on top of each other, just multiplied with these different factors, it will be a solution. So, and then similarly, if we did the same thing with v, we would find this for our solution. And I go through the proof that this is a solution, basically just multiplying this through, acting this operator on this u, you get this. So just, you can go through it if you want, but basically all I do is, this line just comes from doing the matrix multiplication. And then I think I divide by square root of p dot sigma. So I get this, and then I just multiply out, in the square root, these two things. And I get this, and then, cross multiply. Looks like I use the identities of sigma I and sigma j here. It can be written as the sum of the anti-commutator and commutator, commutator and anti-commutator. And then I think this is pi, pj is symmetric in ij, this is anti-symmetric in ij, so this term will vanish. And then the anti-commutator of sigma I and sigma j is delta ij. And so basically what I get is, when I factor everything out, I just get basically this minus m times our spinor should be 0. And that tells me basically that p squared plus m squared should be p naught squared. So it's just the mass shell condition, which is assumed to be satisfied. So, and that is what proves that this is a solution to the Dirac equation. So the important thing is we have our solutions here. And now what we can do is form a basis for our solutions. So we know that we can construct any solution out of these two-component spinors. So what we can do is define a basis for these two-component spinors such that, it's an orthonormal basis. For example, just 1, 0, and 0, 1. And so I could build any two-component spinor out of these basis matrices. But similarly, I can build any four-component spinor out of these kind of basis matrices. So this is US, there would also be a UR. But basically, because the form of the solution takes the form of just, the same two-component spinors stacked on top of each other, we can write a basis for our solution, our fourth spinor, 4-component spinor solutions in terms of these just simple 2-component basis matrices. So, or 2-component basis spinors. So this is one basis spinor, and yeah, again, there would be another one, UR. And any solution could be composed of a linear combination of our 2 basis spinors. So then just some factoids that will come up. So the next thing Tong does is just goes through a few identities involving inner products of our basis spinors. It's not so important that you know them by heart, but we'll just come back to them when we need them in later calculations. But UR dagger US gives you 2 P naught R, delta RS. I've worked that out here. I guess I should go through. So this, I just multiply, I get this, and I can factor out, this to the left and ES to the right, or squiggly S to the right. And I have this, and then this is, so sigma and sigma bar, the spatial parts will be like pi times sigma I, and then this one will be pi times minus sigma I, so that just cancels. So I just have the time part. So I just get p naught times the identity plus p naught times the identity, so I get 2 p naught. And then this inner product, which I already said is delta RS. And then there's a few more. For example, I can define a U bar that, just like psi bar was psi dagger times gamma naught, and so U bar is U dagger times gamma naught. And if I compute this inner product, U bar with U, I get 2 times M times delta RS. And then similarly for V, I have these two relations. V dagger times V is 2 P naught delta RS, and V bar times V is minus 2M delta RS. And then if I do U bar and V, I get 0. And interestingly, if I do U dagger V, I get 0. And then I have these outer product identities. So here, I have U times U bar. So this is like a column times a row, which gives me a matrix, which I can write like this. And then similarly for the V. And these will be used later on.